Hi guys, it's Mr. Kupfer. Sorry I couldn't be there today, but my son Isaac is sick, so I had to stay home to watch him. But don't worry, you still get to watch a fun video today. But it's not the one you think.
What one is it, Mr. Kupfer?
Well, today you're going to watch a video over our notes for this unit.
Oh, wait a minute. That doesn't sound very fun.
Well, I'm sorry. It's just what we need to get done. But don't worry, we'll finish the other video on Friday.
Oh boy, that sounds great.
I'm glad that makes you happy. Today we're going to learn about the Earth, and about the layers that make up the Earth, and how geologists are able to date parts of the Earth.
Oh boy, I want to date the Earth. You know, turnabout's coming up.
That's not really what I meant, Mr. Monkey. I meant we are able to tell what parts of the Earth are older than other parts of the Earth.
Oh boy, I bet the Earth is really old.
You're right. And today you're going to find out how you can determine that.
Yay!
I'm glad you're happy.
Woof woof.
Okay, now let's take a look at the layers of the Earth. The Earth is composed of 4 primary layers. So let's draw an Earth here and go through those layers. The outermost layer is called the crust. It is the thinnest of the 4 layers. It only goes about 3 to 5 miles thick under the ocean and maybe about 25 miles thick under the continents. The temperature of the crust varies from air temperature on top to about 1600 degrees Fahrenheit in the deepest part of the crusts. After that, we have something called the mantle, and this is a very large area of the Earth. And so that's going to go probably down to about, if we draw a circle here for the next layer, this middle part here is the mantle. The mantle is a thick layer. It's denser than the crust, and it's composed of magma, which, as we discussed, is essentially a liquid rock. So there's actually a flow happening inside the mantle of this liquid rock moving around inside of the Earth. The mantle is approximately 1,800 miles thick, and it can range in temperature from 1,600 degrees Fahrenheit to 4,000 degrees Fahrenheit near the center of the Earth. The next layer, 2 layers, are comprised of what we call the core, and the core we break down into 2 smaller layers. We have the outer core and the inner core. The outer core is comprised of liquid, nickel, and iron. This liquid rotates around the center of the Earth as the Earth rotates, and because of the heat, stays in liquid form. The inner core, so this would be what we call the outer core. The inner core then becomes a solid due to the incredibly high pressure at that point. The metals are squeezed together so hard that even though they're hotter than the outer core, they stay in a solid state because of all the pressure pushing down on them. So the inner core is actually solid and still comprised of the iron and the nickel. And so those are the 4 layers of the Earth. Now we will further subdivide the mantle into 2 other layers. The 2 parts of the mantle we'll discuss are the lithosphere and the asthenosphere. The lithosphere is composed of part of the crust and mantle, and the asthenosphere is all just part of the mantle. The lithosphere is thicker and harder than the asthenosphere, and the asthenosphere is less rigid, and this is where the majority of your convection currents are going to flow. So here's a blown up version of all the parts that we just discussed. If you look in the top left hand side, first you're going to see that we have a crust, a mantle, and outer core. And that's what we talked about first. Those are the basic layers of that. When you go inside, then you have the outer core, which is the liquid metal, and the solid core, the solid metal, which is in the inner core. And that's their relative proportion as you go through the earth. Again, if we break down the mantle and the crust, you have your continental crust or an oceanic crust, and then in your mantle you have the lithosphere and the asthenosphere. And that makes up your layers of the earth. Another important skill that geologists need to have is to be able to look at the side of a mountain and determine the age of the rocks relative to other parts of the rocks. And so a geologist would want to be able to figure out how does the age of this crack compare to the age of this crack, or this layer of the rocks as they occur. And so we're going to talk about next the process of what we'll call relative dating. And all we're trying to accomplish in this is to find the date compared to other geological features. Later we'll move into talking about carbon dating, which will actually be able to date something with accuracy. But right now we're just trying to date something compared to another rock or something in the surface. And there are 6 principles that we will use in order to accomplish this carbon dating. So let's go through them. The first is called the law of superposition. And all the law of superposition says is that the bottom layer is the oldest. And this should, I think, make fairly simple sense. If we say had a cup that we were going to pour some sand into, and in this cup I saw that I had some red sand in the bottom, and then next there was some blue sand, and then there was some green sand, it would be safe to reason that I would have had to pour the red sand in first, the blue sand in second, and the green sand in third. And so the lowest layer is always the oldest, and the higher you go up, the newer the layers are. And that's the principle of superposition. The next principle is that of original horizontality. And this says that all layers start horizontal. So as the sand falls, or whatever falls into the bottom, it's not going to fall down and then pile up like this naturally. Excuse me. It will by nature fall into a hole, and as it falls it will end up being a nice horizontal pattern to it. Now if some sort of geological event occurs, then the layers may shift to be vertical or some other position, but as it originally falls, the layers will all form horizontal lines. And that's the principle of original horizontality. The next principle is called lateral continuity. and that says that the layers of sediment extend in all directions when they form. And so that it can tell us, so the layers that you're seeing here, this black layer right there, originally extended all the way across where this river is now. So we know that if this river that we see here is interrupting, it is younger, or happened after all those layers formed. Earthquakes accomplish the same thing. The layers here were all continuous straight across. When the earthquake happened, it created the fault, and so we know the fault happened after all those layers were formed. So again, all we're trying to do is figure out when the events happened compared to other events and say what's newer and what's younger. And so this is the principle of lateral continuity, that all layers will form continuous lines, and that if those lines are interrupted, that means something formed after the layers did. On the bottom here, we can see, just as a review, an example of what we can glean from the principle of original horizontality. The layers on bottom here were originally horizontal. Some earthquake or some other event must have occurred to rotate those layers, and then these layers up here would have formed after that. So we can tell that those top 6 or 7 lines are newer than the bottom 6 or 7 lines, and that that river is the newest of all. And that's the principle of lateral continuity. The next principle is called the law of cross-cutting relationships. And it's very similar to what we just said, I guess, in terms of the lateral continuity, is that folds and faults are younger than the layers they cut across. So I know that this black line here, which was like another rock protruding up from the ground, is going to be the youngest of the 4 there. So this would be the oldest because it's on bottom, this would be next oldest because it's next, and this would be third oldest, and then this would be the 4th oldest, or the youngest of the 4 rocks we see there. So anything that cuts across another layer must be younger than the layer it's cutting across. And that's the principle of law of cross-cutting relationships. Next is the principle of inclusions. Inclusions are other rocks that are embedded in a rock. And so what happened here is that a newer rock formed around an older rock. And so as we see these little specks of rock inside this other seemingly newer rock, we know the inclusions in there are older than the rock that formed around it. And last of the 6 is called the principle of faunal succession. And that means that if I can date a fossil in a certain layer, I can then say that this whole layer is the same age as that fossil. And so fossils can be used to identify relative age of layers of rock. And so once we get to the point where we can carbon date, I can say, okay, this fossil is 400,000 years old. I can then determine that, you know, the dirt that formed on top of it must be younger than 400,000 years, and the dirt that formed below it is older than 400,000 years old. And same with this dinosaur. If I can determine this dinosaur is 200 million years old, I can determine the relative age of all the layers around it. And those are the principles and practices we'll use when performing relative dating.